when Galileo invented the telescope, people didn't want to look through it. And that also makes me think about a lot of the stuff happening in science where people refuse to look at certain theories.
For decades, reconciling quantum theory with gravity has been the holy grail of theoretical physics. But what if the path forward isn't through ever more convoluted mathematics, but rather through ingenious experiments we could perform right now? Professor Ivette Fuentes, the close collaborator of Roger Penrose, is proposing just that. Groundbreaking tests using ultra-cold atoms and quantum technologies that could probe the ostensibly quantum nature of spacetime. Yet, despite its potential, many researchers in the field are hesitant to pursue these ideas. Is it the allure of purely theoretical work, the inertia of established research programs, or simply the challenge of breaking away from fashionable thinking? In this episode, we'll explore Professor Fuentes' inventive approaches to testing quantum gravity and why they're being overlooked by much of the physics community. Professor Ivette Fuentes, it's a long time coming. I'm super excited to have you on here. The audience, it's going to be a treat for them. They don't realize it right now, maybe, but the audience is in for a great treat. So thank you, and the floor is yours.
Thank you very much. I was just telling you just now that I love your podcast and I listen to it, see it very often, let's say. So it was very nice meeting you just now because I felt that I've met you forever. So this feeling
Wonderful.
of after seeing you often in the evenings, and then it's like, oh wow, that's you there. So that was really very nice. And I was also telling you just now that I saw some of the podcasts that you were talking about string theory.
Physics is like whack-a-mole. Einstein said, I have this idea. Acceleration and gravity are the same. Problem, how do I make this work with a scalar field? So that's like a little mole that comes up. He whacks it down. He says, okay, maybe it was a mistake to unite space and time. But then problem crops up. You have to introduce a variable speed of light. So then he's like, okay, let me knock that down. Forget about scalars. Let me introduce tensors, a different mathematical object. You knock that down. In order for string theory to work, it needs to be 26-dimensional. And it only had bosons at this point in the story. Okay, why don't we add something called supersymmetry? So we knock it down. Okay, cool. Problem. There's still many types of string theory. And now there's 10-dimensional, not 4-dimensional, but it's some progress. Okay, solution, you combine some heterotic strings. Okay, problem, we still have 5, and we have gauge anomalies.
And how when one works in foundations of physics and in unification, there's like that, I think you mentioned that people say it's like the only game in town, and how there is this sort of social pressure to work in the field. So I'm working at the moment in the unification of quantum mechanics and general relativity. Like this is kind of really focusing on that problem. It's a more recent thing. I still don't have actually my results available, but they're coming up. Of course, not the full thing, but I think a nice, interesting step I think we managed to achieve. But I come from a very different sort of place. Mm-hmm. And I thought that maybe the story of that could be interesting in the light of the things you've been discussing.
Yes, and I've been looking at your research in the evenings as well. And so this is a wonderful experience for myself, and I would love for the audience to get familiar with you. So please go over your recent results.
Great. Yes. So I became interested in the foundations of physics as a student at university. I had a teacher, Luis de la Peña, who I enjoyed. He was teaching me quantum mechanics, and I particularly like his class because he talked a lot about interpretations of quantum mechanics. So I was really fascinated with that. He was very generous because at some point I approached him and I said, I want to work with you on this topic. And he said, you know what? It's been very difficult for me. It's been a really difficult path, and I don't want that for you. So I would suggest work on something more sort of mainstream. And if you're still interested when you're grown up, let's say, you can come back. And I think that is somehow related to what you're saying, that he took a different path. And he found it extremely difficult. And he wanted to spare me of that. I think he could have just said, yes, great, a good student, come and work with me. And instead of that, I think he was very generous by saying that. So I think, well, what I approached him also because I wanted to go to Fermilab. There was like the possibility, a competition to go and spend the summer there. And I asked him for a reference letter, and he said, "Why would I give you a reference letter?" And I said, "Well, because I got like A's in all your classes." He said, "Well, many students do that." And then from there we just went on talking. And what I told him was that I was finishing my degree and starting to see what I wanted to do. And I mentioned to him that all of my classmates that were interested in theory were actually going into string theory. And that I actually, when I learned about string theory, like all of my classmates, I was absolutely fascinated with it. I think this is a beautiful idea that we treat particles like point like systems, and then the idea that there's another dimension or more dimensions, there are strings, and how you could unify the notion of different particles in this way is beautiful, and I loved it. But then once I got more into it, and sort of issues started to pop out, especially the many dimensions, then I thought, this reminds me of the epicycles. And let me explain, what I meant. So I'm sure that most of people in the audience are familiar with this. But back in the time, people wanted to describe the trajectories of planets. But back then, people used to think that they had to follow, nature had to follow circles, because circles is the perfect figure. It's a shape. It's really interesting how we get into these ideas and we get so stuck in them, right? And those are the ones that don't let us make progress. So we can come back to that maybe later, because we've been trying to unify quantum mechanics and general relativity for more than 100 years. And we're probably stuck with something equivalent to the perfect figure, and we're unwilling to let go of that. And maybe we can talk about later about that, because there's like some ideas. Actually, I think that maybe even consciousness could be sort of something missing in the equation, let's say.
Oh yeah.
So if you try to describe the trajectory of a planet using circles, well, first one was not possible. People say, I remember I also heard you talk about how you get a problem and boom, you bang it and you fix it, and then another one comes out and you bang it, and so
right, the whack-a-mole.
Exactly. Yeah, so you do that with the circles, and okay, you add another circle, and that doesn't work that well, so you add another one. And well, back then people used to need something like 600 circles to more or less describe the trajectory of a planet. And then came Kepler and says they're not circles, they're ellipses. And boom, no more necessary to hit things with a hammer anymore. It just falls in everything beautifully, right? So when I heard about, when I looked into string theory with a bit more detail, not much, I very soon felt this reminds me of the epicycles. It can't be right. And I told that to my teacher, to Luis de la Peña, and he smiled. And he said, "I'm going to give you the reference letter where you want to go."
That's interesting. What was it specifically about what you said that changed his mind?
Well, I think he liked that I was so, in a way, critical of string theory, and that I was not going where everybody else was going, because I just had a feeling this is not right.
Now, didn't he mean to go into string theory when he said that you should go into physics in a more mainstream manner?
No, then let me tell you what that is, because that was another important point. When I was finishing my degree, I think also like many students, I was also sort of in love with astronomy. No, that's always like many students go also in that direction because it's just so attractive. And I did an undergraduate thesis on Seyfert galaxies. And I enjoyed that very much. But after my work, and my first paper is on Seyfert galaxies, I thought, well, I could spend the rest of my life studying these beautiful objects. But something is missing. I didn't have it I was so aware of it like I'm now. But what was missing for me was that studying these beautiful objects, I felt were not really bringing me to the point of asking questions like, what is the fabric of reality?
Okay. So something was missing, not with the galactic data, but with what even the most ideal answer to any astronomical question could provide, to the foundational aspects of the questions at your heart.
Yes.
Okay.
Yes. Somehow I felt like studying, I could spend my whole life studying Seyfert galaxies, and that would probably be a lot of fun. And I would get some, I already had like a really good paper. It was a letter and everything. But I felt like I'm not going to be able, if I go in that direction, to really focus on the questions that I'm really interested in.
I see.
And I guess, I was more interested in understanding sort of more foundational questions, like deeper, what is reality about? So I was in the cafeteria at the university, and suddenly a colleague of mine, I'm still working with him, Pablo Barberis, ran into the cafeteria when I was doing my homework, and he said, they demonstrated quantum teleportation. And I was like, what? That was Anton Seilinger's experiment. But then it would play a role in my life as well, because I ended up being a visiting professor in Vienna within that group for three years. But back then it was like, some people in Europe demonstrated quantum teleportation. And Paolo also told me, you know what? They also managed to trap single particles, single atoms in an ion trap and in a cavity. And I remember my teacher, Luis de la Peña, used to say quantum mechanics is a theory that doesn't apply to single particles. In experiments, we're always doing experiments with an ensemble and many particles and stuff like that. So then when I heard that, I said, okay, that area is going to get super interesting. Because if now they can do experiments with single atoms, we will be able to address some of these fundamental questions. And that's where I thought, okay, that's the right thing to do. So when I had already a little bit talked to Luis about that, and when I told him, what about quantum optics? He said that's excellent. So I went to Imperial College to work in the group of Peter Knight. And when I arrived, with the idea of doing quantum optics, and when I arrived there, everybody was working on quantum information and entanglement measures and so on. So I ended up doing a PhD in, let's say, in the interface of quantum optics and quantum information. That went really well. I did very well. And then from there, I went to do a postdoc at the Perimeter Institute.
Yes, my neighbor.
Yeah, yes, exactly. You're in Toronto, right? When I arrived there, it was really exciting because I think I was the first or the second postdoc to arrive there to work in quantum information.
Cool.
The institute wasn't established as it is now yet. It was the building was like the old post office in Waterloo. It was so cool. We had like sofas and like a bar and a blackboard, and we sit like at home, and it was really like a fantastic experience. But when I got there was one group in quantum information, a very small one, and then there was string theory and loop quantum gravity and foundations of physics. And I started so we were such a small group, I started to attend the seminars in gravity and quantum field theory and Curt spacetime. I got very jealous. I felt very jealous. I thought like, oh gosh, I'm missing out on something.
Because you were in the quantum information section?
Yeah. And people in quantum information were talking about quantum cryptography. The idea of quantum cryptography is beautiful. But if you work on that, then it's again like, oh, how do you make a hack and how do you fix it? And again, you get lost in those things. And I was thinking, no, this is really not for me. So I thought maybe I change and I work on general relativity. But I had already made a few jumps. No, I went from astrophysics, a paper there, to quantum optics, and then I have a paper on quantum computing. What am I going to do? And I thought, well, maybe it's not a very good idea. And I started, without knowing this was kind of a new thing, I started like the innocence, as a young researcher, I started to mix them. So I wrote a paper that's called Alice Falls into a Black Hole Entanglement in Non-Inertial Frames.
Okay.
It's my most cited paper.
Wow.
And it really sort of opened a door for me, let's say, in the scientific world, because you were also talking about how difficult it is and how competitive it is to get, a name and known and a position and so on. So what I did is that I applied what I had learned in Imperial College about measures of entanglement to quantum field theory in Curt spacetime and to eternal black holes and so on. And it was a very new thing to do. Now there's like a field more or less established in that direction that people call it relativistic quantum information. So I was having a great time working on that. But it was all very academic. It's like, entanglement in black holes and things like that. I still felt that I'm now getting lost in maths and getting lost in maths. Yeah?
When you say it was too academic, you mean too theoretical, removed from experimental underpinnings?
Yes, exactly. Yes. And then I got into this idea that, I want to bring this stuff to a point where I can do an experiment. I mean, of course, not me, I'm a theoretician, but propose an experiment. So I hired a postdoc. His name is Carlos Sabin, who was someone doing theory, but very close for experiments. And he was working with superconducting circuits and stuff like that. And it was really funny because I just thought, I didn't even have a clear idea of how we would get there. I just said, this is where I want to go. And we together started to work with quantum metrology, applying it to quantum field theory in Curt spacetime. So now that's going to go into my slides. Sorry for the super long introduction. But I thought it was relevant to what you were talking about recently. And I actually managed to start proposing experiments. Some of them, at least partially, have already been tested, and the experiment have been done. And that became sort of my path, studying quantum and relativity, but really proposing experiments. I was not working in unification because I was working with quantum field theory in Curt spacetime. So I'm going to tell you a little bit more about that in a moment. And then by doing that, that finally brought me to an idea that is my own, inspired by the work of Roger Penrose, who I talk to him very often. And then I managed to kind of come up with a theory that can be tested in the experiment. And we're going to do that very soon.
Cool.
So that's the kind of the story and of why, my talk, which is also about unification, comes from a very different perspective, comes from someone who's background is in quantum optics and quantum information, and looking at experiments and then sort of trying to see what can we learn from these theories and their interplay, and try to make theories, informed by the experiment.
Wonderful. Thank you for that introduction. I have two quick questions.
Yes.
Maybe they're addressed in the talk itself, but so you were in, firstly, astrophysics, then you went to quantum information, then you saw some talks on general relativity, and you thought maybe you want to go into that field, but you said it would be too much of a jump of you jumping back and forth. Mm-hmm. But would it be? Because astrophysics does it not already use general relativity? So how much of a jump would that be? It would be like jumping backward rather than jumping to the side, no?
Well, it could have been a bit like jumping back, but the work that I was doing in astrophysics was not really related to general relativity directly.
Ah.
It was more, I was doing statistical studies on how companions of Seyfert galaxies could trigger the material of the galaxy to go into the black hole and so on. So yeah, I guess because of the type of analysis that I was doing, it would have been like another jump.
Okay. Cool. And then now you also mentioned that you work on quantum field theory and curved space-time. Now, some people would see that as unification because general relativity has something to do with curved space-time.
Sure.
So can you please delineate those two?
Yes, actually, I'm going to do that in my slides. So,
Great.
I mean, but very quickly, that's the beauty of quantum field theory and curved spacetime, is that it allows you to study some, let's say, quantum effects and relativistic effects. They interplay in some scales, but it's not the full theory. It doesn't resolve actually what I think is the most interesting question. So yeah, let me get started, and I'm going to get there very, very soon.
Wonderful. Take it away. The floor is yours.
Okay, thanks. So, yeah, there are many fundamental questions that are unanswered and very interesting ones. And I wrote in this slide just a few that I find fascinating, and maybe some of them I work on as well. So, for example, what is the nature of dark matter? That is a big one. So, yeah, well, questions like, is dark energy driving the accelerated expansion of the universe? What's the physics of the very early times and cosmology? Does the equivalence principle hold for quantum systems and so on? There's many, many interesting questions and fundamental physics that don't have answers. And underpinning our difficulties to find answers to these questions is our difficulty actually to unify quantum mechanics and general relativity. I went to a conference a few years ago, and it was all about how can we use quantum experiments for fundamental physics. And many of these fundamental questions came up. And then someone in the audience, a colleague of mine, got up and said, well, but nobody is addressing, kind of the elephant in the room. And what's the elephant in the room? Well, that, we for more than 100 years have tried to unify quantum physics and general relativity, and they're incompatible. So how does that affect all these other interesting questions? And then that's where I think I felt, yes, that is a real interesting question to answer. So this is like the very typical cube that one sees in theoretical physics, but I just, a bit designed in a different way, where you have relativity on one axis. So that would be c, the velocity of light. Then gravitation on another dimension, that would be the gravitational constant G, and then quantum physics would be h bar. So this cube here, I'm trying to show that, well, we have some pieces of the puzzle. So there are parts of the theories that kind of answer some of the questions or work well in some scales. So, and we have a lot of work done in the last years in different, pieces of this puzzle, but we don't have the whole picture yet. So, quantum field theory and curved spacetime, I would say, is like one of these big pieces of a puzzle, but it doesn't do the whole thing yet. No, so I'll go into why not in a moment. Okay, so this actually title of this slide, should we quantize gravity or gravitize quantum theory, comes from Roger Penrose. And what he means by that is, should we keep the principles of quantum theory and modify general relativity? That's what we understand more by quantum gravity. Or should we do the contrary, keep the principles of general relativity and modify quantum theory? So I guess, like most people working on the unification, maybe follow the first line of quantizing gravity. But Roger thinks differently, thinks that quantum theory has a problem anyways, which is the measurement problem. So he supports more, let's say, the route of keeping the principles of general relativity and then trying to modify quantum theory to bring them together. Now, we both agree that it's more likely you have to modify both of them. But let's say Roger would always give more priority to general relativity in that sense. So I was writing here in this slide like a few things about both theories. So let's go first to quantum theory. Like same as in classical physics, time is absolute in quantum theory. So clocks tick at the same rate for any observer independent of its state of motion. And this comes from the theory being invariant under Galilean transformations. So the underpinning transformations are Galilean transformations, just as in classical physics. So in the same, that inherits that space and time are very different notions. The Schrödinger equation treats space and time completely different. It has one derivative in time and two in x. It treats time like a parameter, and then positions can be quantized, and you use operators, which are completely different mathematical structures, no? So then already from there, they would be incompatible with the relativity.
And just for some clarification, quantum theory means quantum mechanics and not quantum field theory.
Yes. I guess because of my background, I use that more when I say I like to use actually more quantum physics, but that I'm just talking about like Schrödinger equation. Fields is like a step more. No. Yes. Well, then in quantum theory, we have the superposition principle. So particles can be in a superposition of two distinguishable locations at a time. And then, well, this is what Roger calls, many people call the measurement problem, but in quantum theory, the outcome of measurements is probabilistic. Fundamentally probabilistic. And then when we want to measure, let's say, space or time, we have an uncertainty principle that tells us that if you measure positions very precisely, then you cannot simultaneously measure momentum and so on. Also, it's kind of a bit of a summary of some of these, let's say, fundamental principles of the theory.
Yes.
Then on the other hand, in which way they're different and why are they incompatible? Well, in relativity, time and length are not absolute, are observer dependent. So the underlying transformations in relativity are Lorentz transformations. And if you look at they mix space and time. So let's say the more radical thing I think that we learned from Einstein is that space and time are not different in the way that we understand them in classical physics and also in our experience, right? If you tell anyone space and time are like a bit of the same thing, people would be shocked with that. But that's what Einstein showed us, that they actually belong together in a higher dimensional object, which is space-time. And they're both dependent on the state of the observer. And then you have in relativity, if you have gravity, for example, it curves space-time. And then if you look at two different points in space, you can see that time flows at different rates at different points. So already there you can see that in relativity you have to treat space and time on an equal footing. So let's say equations, if you have that you're having a second derivative in space, you should also have a second derivative in time. So that you can already see how that is already incompatible with quantum theory. And so a little bit also the question of time is at the heart of our difficulties to unify the theory. And then you could think about things. How would you see if a mass is in a superposition of two different locations, and then time flowing at different rates. I mean, the Schrödinger equation has only like one derivative in time is one time. You cannot think about such questions yet with the theories that we have currently, no? Another thing, just to finish with the slides, like in relativity, we don't have this thing about the outcome of measurements being probabilistic, but it's a deterministic theory in that sense, and we can measure space and time as precise as we want. But in my opinion, the most interesting question that we have to answer is what happens when we have a massive superposition where the mass is in a superposition of two different locations in space. And this is something that you cannot answer with quantum field theory in curved spacetime, because, I'm going to go more into that later, but the theory assumes that you have sort of a fixed background, so a fixed space-time metric,
yes,
which is a solution of Einstein's equations, but the fields themselves, or the mass itself, doesn't curve it. So you couldn't answer this question. I think this is really an interesting and important question, because we know, for example, from the experiments that you can have the electromagnetic field in a superposition. So you can take an electron and put the electron in a superposition, and then you can see that the quantum fields generated are in quantum states. So we were talking about quantum optics, and quantum optics has been, a theory that has been tested in many, many experiments. And we know that the electromagnetic field can be in quantum states. And now the big question is, can gravity also be in a quantum state in this sense? And if the mass is very small, yes, because the moment that we have, let's say, an atom in a superposition, in a way, the gravitational field produced by the atom is also in a superposition. But I think the big question is more like if that's a stable situation or not, no? And that's where Roger, and I'm going to go more into detail of that, comes in and says, you can, but that is a very unstable situation, and gravity collapses the wave function, which would then resolve the measurement problem. And that would explain more like the transition between the classical world and the quantum world. That would explain why we don't see, let's say, this cup in a superposition of here and there, and so on. I'm going to talk more about that in a moment. But I guess my point here is that I think this is the most interesting question to answer. And there are good reasons to believe that gravity could act different to the other forces. And that is because gravity is the only one that has an equivalence principle. So there is not an equivalence principle for the others. No, so in the equivalence principle, if you're in a lift and you don't have any way to look at what's happening, so in a box outside, you could not distinguish when you feel an acceleration, if that is because you're in the presence of a gravitational field or just because the box is being accelerated. And that is something that is specific from gravity, and that could distinguish gravity from the other forces. So that is something also that Roger argues that might hint at gravity being fundamentally different. Okay, so I mean, obviously the question is very important per se, but also, as I said, it underpins other very interesting fundamental questions in physics. I found this picture, the one with the stars and so on online is a very famous one. Actually, one of the things I lost because I lost my talk just a few moments ago were all the credits to the images. So I'm sorry I had done that detail and so on. But when I saw this picture, I liked it very much. And it made me think about how was it when we were trying to make sense of, let's say if you want cosmology, of where are we? What's this, let's say, world that we're seeing? What are those points in the sky that appear at night in a way? What's the universe? And so on, without instruments. No, so I can imagine, I like to have a romantic image of that, of, people sitting around the fireplace and looking at the sky and trying to make sense of where are we. Without the telescope, you can imagine how hard that would be, and what sort of theories humanity came up with when the only possibility was to use our own instrument, that are our eyes, and look at the sky. Then Galileo invented the telescope. It's very interesting that as well, that when Galileo invented the telescope, many people didn't want to look through it. And that also makes me think about a lot of the stuff happening in science where people sort of refuse to look at certain theories. That reminds me, I also heard you talk about that, and you were talking about, well, I mean, if you're working in string theory or in loop quantum gravity, don't you have sort of the moral responsibility of looking at what other options are there?
Yes.
Right? And that, I think it's like refusing to pay attention to competitive theories or other ideas. I think it's a little bit equivalent, like refusing to look through the telescope.
Interesting.
No, somebody else comes with a new invention, says, look at what's happening. You say, no, I don't want to even look. But that happened. Now, since then, telescopes have developed incredibly. We have amazing, like the latest pictures that you see are just like amazing what they can do. But well, now with very good instruments, we could look at the sky. We can look really into the past of our universe, and then see that, oh wow, it looks like the universe is an expansion, and so on. And we can come up with more meaningful theories, with better theories, thanks to those observations. Same if you think about the microscopic world. So the Greek came with the idea of the atoms. But again, it's not until you build a microscope and you can look into the microscopic world that you can do better atomic physics. So I'm trying to make the point here about how important have instruments been in us making better theories and understanding things better.
Mm-hmm.
Right? So when it comes to these scales where quantum mechanics and general relativity interplay, we're blind. We don't even have our instrument. We don't even have our eyes. We don't have anything.
Uh-huh.
So how do you go about, right, when you do that? So I think I understand string theory and loop quantum gravity and many of these very mathematical approaches in that sense is that you do what you can what you have at hand, and what we're able to do is super powerful studies with mathematics, because our mathematics is very developed. And you were also talking about that, how actually string theory has allowed mathematics to develop so much, and so much we've learned about mathematics thanks to those theories. But when you come up with theories and mathematics, well, there's many possibilities. You can make many theories, almost as many as you can think about. But which one is the right one?
Mm-hmm.
I can make a theory, but then I need to see if actually nature behaves like my theory predicts.
Right.
And then I can have a competing theory, a different one, and which one is the right, maybe even contradicting the two theories in principle and their predictions. How do you know which one is the right one? You need to go to the experiment. You need to go to those instruments. And I'm going to argue that we sort of have them already, and we need to start looking through them for resolving these questions of unification.
All right.
What I think we want to do is to get into this cycle in which, let's say, you come up with an idea. So this would be philosophy and creativity. So going back to the example of the atoms, right? So the Greek came up with using philosophy and creativity and so on with the idea that there must be something in matter that you cannot keep dividing. So there must be this unit, and the idea of it cannot be divided anymore. So the idea of an atom. Then, well, if you want to observe an atom, well, that's like a really long way around, right? But you have to do some theory about what is an atom. So, well, a very, very long time after, people started to develop better theories of the atom. Or, for example, I don't know, the pancake theory, where you had some, electrons raisins in a pancake, or even better, Bohr's model, where you have like the nuclei and the electrons going around like if they were like planets around the sun, right? So you need to create some theory so that you can build an apparatus and then observe this idea that you had, that there's atoms. Because you cannot build a machine or propose an experiment or develop a new sensor without some sort of theory. Your theory might be wrong, but at least it gives you, a starting point to say, okay, now I'm going to build this machine. Then you build, let's say, the microscope, and you look through it, and then you get some sort of signals, and at some point, like detectors click or something like that, and you say, oh, there's my atom.
Mm-hmm.
Right? So, and then you might then find out that your theory was actually not very good, but then you can improve it and modify your apparatus, and then you get into this really good cycle where you can start making better theories all the time and verify them into the experiment. So this is what happened with quantum optics.
It seems like this is what happens with the general theory. So if I'm understanding you correctly, it sounds like what you're saying is you're initially on your couch or in your shower, an idea comes to you, it's an intuition, you then formulate it with words, natural language, you then have to formulate it into mathematical language, and then you have to check that against quote-unquote reality with an experiment.
Yes. So you propose an experiment, and the experimental proposal, that's what I work a lot on in experimental proposals, is also mathematical, right? I have to write down my theoretical proposal. This is your Hamiltonian, and these are your measurements, and this is the precision. And I claim that you should be able to build this device, and I'm going to show you like one of my works in that talk about, of course, of my proposals to do that. And then you need to build it and then check.
Okay. And you were giving a specific example in quantum optics. Please continue.
Well, with quantum optics, there's this very healthy cycle, and I think that's why there's been so much progress in quantum technologies, is because this happens all the time. People come up with an idea for a sensor, and they write papers about it. They make a proposal, then an experimental group gets a hold of it. They work together, and boom, they show that, and there comes again the cycle, and it's a wonderful field. Mm-hmm. And I think I was used to that. So when I started to work on Alice falls into a black hole and entanglement in black holes, I was like, oh gosh, I can't check if what I propose is correct, because there's no way to make a measurement in a black hole. And that's how I started to say, no, I want to do theory that it can actually, still work at the interplay of quantum mechanics and general relativity, but that I can test in the lab. So that is like, my group and most of the last, I don't know, maybe 15 years, that's what I've been working on trying to propose experiments or develop new sensors that will reach these scales where quantum mechanics and general relativity interplay, so that we can then get into this cycle.
And what is FP?
GR, quantum theory. I forgot. What did I put here for? It's an old slide. So quantum theory for sure. GR. And fundamental physics is fundamental
Okay.
physics. Yeah, maybe that's a really funny figure. Okay, so when I was at university and I learned about quantum mechanics and general relativity back in the day, well, for example, Luis de la Peña would say quantum mechanics only applies to a few particles and at very small scale, so where electrons and atoms live. And general relativity applies to the large scales. Starting with from GPS, to get the precisions we have, we need to make corrections due to general relativity. So the proper time on Earth is different from the proper time in a satellite, and you need to make corrections to have the precisions that we have in GPS. So it would start, say, from those kind of scales onwards. I mean, we know that general relativity doesn't really apply to all these scales because, the rotating curves of galaxies, the observations there contradict the predictions of general relativity. And from there, the whole of the idea of dark matter comes about. So it doesn't really apply. But let's say generally you're a student and you're told quantum physics applies to the very small and general relativity to the very big. Now, because of this circle that I was telling you about, now the experiments in quantum technologies they developed amazingly, and now it completely challenged this picture. And I want to tell you a lot about that. So I'm going to talk about three things. One is long range quantum entanglement. So what are the longest distances at which we can prepare superposition states or entangled states and so on? And how can we study such situations? And what can we learn about the interplay of quantum mechanics and general relativity through long-range quantum experiments? Then high sensitivity. Actually, when I started to work on using quantum theory, I wanted to, measure some relativistic effects. Some of my colleagues in general relativity were laughing at me because they were saying, well, at small scales, forget it. Space-time is a bit flat. It's completely flat. Sorry. You won't see anything. I'll show you that that's not true. And then
interesting.
And these are already experiments that have reached relativistic effects. We're just not looking through the telescope right yet because, I'll tell you more when I get there. The one that hasn't gotten to scales where gravity kicks in an important manner is large mass quantum experiments. So I also want to tell you about the progress in that direction.
Please, yeah.
And how far we are from being able to see, for example, if gravity indeed collapses quantum superpositions and so on.
I have a quick question, if you don't mind.
Yes, sure.
So with GPSs, they're using an atomic clock, I presume, which is something that's a quantum phenomenon, and then they have to correct because of general relativity. So do people see that as an interplay between general relativity and QFT or quantum mechanics there?
I'm going to actually go into the details of the question that you just asked me. I have a slide on that, so it's like a really
wonderful
question right to the point. But the short answer now is that people brush the questions in a way out. They find solutions which I don't think are solutions. That they're let's say, well, maybe approximately work, but actually are not the right thing to do if you want to be, let's say, rigorous with what you're doing. And actually that gives you the opportunity to answer these questions. So I have a slide on that, exactly the question that you're asking me.
Great. We think alike.
Yes. I noticed that before you from the podcast in many ways, actually.
Cool.
Okay, so let's talk about the long-range experiments. When I was a student, when Pablo came, my colleague, into the cafeteria and told me they demonstrated quantum teleportation in the lab. That was in Vienna. That was Anton Seilinger. It was in a tabletop experiments. So you have like a table that could fit in this room, let's say, with mirrors and lasers and so on. And that's how experiments look like in those times. Then Anton, some years later, wanted to see how big can the experiment grow such that you still have entanglement. So this is entanglement between photons. Okay. And he was able to demonstrate entanglement across 2 different buildings in Vienna. So, well, that was very promising. So he said, well, let's keep going. And then in 2011, he was already doing the experiment across 144 kilometers and in the Canary Islands.
Oh, so they're not physically connected tubes that connected the 2 buildings, nor in this 1,000 kilometer case.
Well, there are many experiments that are connected by a waveguide. People do experiments like that, but no, these are like free space experiments.
Interesting.
Yeah, they're beautiful. They're very, very interesting. So Anton had a student from China who then moved back to China, and then he's made a lot of progress there, and together they launched a satellite which is called MICUS, which is completely purposed to study quantum entanglement and teleportation and cryptography and so on. So they launched it in 2016. And then they've demonstrated entanglement across thousands of kilometers.
Right.
So that's very interesting. No, because this whole notion of quantum mechanics applies to very small scales. Now we see that that's not the case. Well, of course, photons are, they're not massive systems or anything like that. But already, I think this starts showing that this division of what are the scales where quantum applies and where it's different, maybe in some senses, as we first thought it would be, no? But well, I mean, what's very interesting is, like, as I mentioned before, at the scales where satellites operate, relativity kicks in. Again, the proper time of clocks measured on Earth is different to the clocks that you said that are in a satellite. So you have to take into account at least a gravitational redshift. So this is like special relativistic effect, but more than that. So that is something that I've been very interested in. I have a whole series of papers that use quantum field theory in curved spacetime to describe the spacetime of the Earth using, for example, the Schwarzschild metric, which can be applied to this case. And then you describe the photons and the quantum states that travel from Earth to a satellite or between links in between different satellites. As using quantum field theory in curved spacetime, you can solve the equations and then construct wave packets and study how let's say if you send a wave packet from Earth to a satellite, how would this be modified due to the curvature of the space-time under light? So this is no longer just special relativity using gravitational redshift. That was what people were using. We showed that if you use quantum field theory in curved spacetime, you could actually go beyond that and really see how the curvature of space-time affects for example, we wrote some of these papers and we said, this is what the curvature, how would it affect, for example, quantum teleportation or quantum cryptography? And then you could turn things around and use the fact that these states are modified to actually estimate the space-time parameters of the Earth using quantum metrology.
Okay,
so
cool.
That's of area of interest, and I've written a series of papers in that direction, more or less, trying to answer this sort of questions. But you see, these are experiments that already are taking place. And actually, there was a group working in Germany that once the whole group came to visit mine because they had some results they were not understanding, and they using just the gravitational redshift, and they wanted to see if there was more to be understood from our work. So this is, yes, a instance where you do see that some interplay between quantum states and the spacetime of the Earth. The experiments reach those scales, but there's very little apart, from our work. I don't see that there's many more things, or the experiments actually they take into account the gravitational redshift, but they still have to test this sort of things. Now, quantum field theory in curved spacetime has not been demonstrated in the experiment. Quantum field theory, yes, so many times. That's what CERN and Fermilab and all of these experiments are about. But when you have gravity included, it still needs to be demonstrated. So some of these predictions that we make could start giving you some hints that quantum field theory in curved spacetime, let's say, it's a good theory for these scales. It would be very nice to check that.
So for the audience member who's thinking, how does this work logistically? Do you have to petition for time from this satellite, or do you have to ask the people who are in charge of the satellite to perform an experiment? Like, how does it work?
Well, I actually belong to a group that was sort of a consortium in which they worked together with the theoreticians, with the experimentalists, and the group sort of discussed about which would be things that would be interesting to study. So the theoreticians would say, well, we would like to test this theory. Let's say I had a colleague, Tim Ralph, who came up with a new theory that sort of used quantum field theory in curved spacetime, but went beyond that and take into account closed time-like curves.
Right.
And then he proposed an experiment. And then the group found this interesting from a theoretical point of view. But the important thing there was that the experimentalist found it feasible to do the experiment. And the experiment was done. And the experiment didn't find evidence of this sort of new theory. But you see, that is the sort of thing, is great. That's the sort of thing you want to be doing, that people are creative, come up with new ideas. Again, the circle, cast it in language first, then in the language of theoretical physics, which is mathematics, make predictions. The experimentalists go test and they say, well, yes or no, and then you go on. So I think that there are groups like that, and usually also what we do is that we get together theoreticians with experimentalists and make a proposal that might or not get funded. Of course, with space-based experiments is more complicated. I have actually been approached by NASA a few times, and they asked me, do you have an experiment that you think we could do? But the things I've been working on lately are more things that you could also test on Earth. And then you need to justify the expense. But, well, I did point out to these papers, and I said, well, I think it would be great if you could test some of these. But I haven't heard like, oh, yes, we're doing it or anything like that yet. Okay, so now we go to the clocks question that you were asking me and the very small scales. So yes, like you were saying, quantum clocks are the most precise clocks that we have, and actually that is what we use to, distribute clocks in the planet, and you need to synchronize very well computers and airplanes and all sort of things that we need very we for our instruments, we need very precise ways of measuring time, and these are done by atomic clocks. So, very roughly, how would an atomic clock work is that you have many atoms here, for example, strontium, trapped in an electromagnetic potential. So the sample could be like atoms that are cold, so that means they move very little, and they're within some sort of volume, so typically it's like a millimeter, and so on. So the energy levels, the internal energy levels of atoms are very sharp. So let's say between the ground state and the excited state, the energy is very precise. So that you can use this as a frequency standard that gives you like the ticks of the clock very precisely. So you shine a laser and you excite the atoms and so on. And well, that's more or less what you use. So there was this beautiful experiment done many years ago by Dave Wineland, who got the Nobel Prize for trapping ions in an iron trap. He did this experiment after, in which he would take an atomic clock and then sort of put another one or just like move his clock upwards. I'm not sure actually what he did, but he demonstrated time dilation at 33 centimeters. So before we know, okay, we can see time dilation if we're in the Earth and then in a satellite. We know that. But now he said, look at these scales of 33 centimeters. You can see time dilation already.
And that time dilation is just due to the gravitational potential difference?
Yes, due to the Earth. Just from the gravitational field of the Earth. So basically, you're demonstrating that the space-time is curved.
Yes.
No? So that's really amazing. And so, I mean, these clocks are super precise. They have like a systematic uncertainty of, they can reach 10 to the minus 18. That means that the error is 1 part in 10 to the 18. So that would be more or less like in years. I used to have it here because I forget, but the clock would lose precision would lose 1 second in something like 30 billion years. I had the number here exactly, but I now lost it. But more or less, no, that precise they are. And that's what I was telling my colleagues in general relativity that found it funny that I wanted to measure these curvature things. I said, no, look, I mean, these things are so precise, that is not unthinkable that we can actually measure general relativistic effects at very small scales. So I was talking to Patrick Gill. So he's a colleague of mine who works at the National Physics Laboratory. So that is like the institution in the UK where they do all these, with the Metrology Institute, where they do all these standards of frequency and the different units and so on. So he's working with the quantum clocks, with the Helen Margolis and so on. And I was telling them, you know what? Soon you're going to have a problem because you're going to get the proper time at the bottom of your sample with the proper time at the top is going to be different. And he was saying like, yeah, but we're not too worried about this now. And so 6 months later, that happened. 2 papers came out showing that, they could see time dilation. Well, first there was like this 1 centimeter and then even in 1 millimeter.
Wow.
So now if you think about the quantum clocks, the clock in the atoms in the bottom see a proper time different from the atoms on the top. Yes.
Super interesting.
But okay, still, people working on clocks might not be that worried.
When did this result come out?
That must have been a couple of years ago. Okay,
so fairly recently, 2020s?
Oh, yeah. Yeah.
Wow.
Maybe this is actually... Look, this is from this paper I put here is one of the papers, and it says published in 2022. I think it might have been submitted in 2020 or 2021, but it was published very recently.
Sure, it's still cutting edge. Yeah. I see.
So it is not a problem as long as the atoms are independent, because then what you can do, which is what we do with time dilation with GPS, is like we know how that changes, so we can theoretically correct for it, and then you just take that into account, and you don't have a problem. Okay, but now people want to make these clocks more precise and beat this 10 to the minus 18 uncertainty by entangling the atoms. Because we've showed in quantum metrology that if you have entangled atoms, you get, a precision, instead of going like 1 over square root of n, it's 1 over n. It's called the Heisenberg limit. And this makes things much more precise. Okay, so if you do that, then you have a problem. Then you you bang your head with quantum mechanics and general relativity being incompatible. Why? Because what time are you going to use? The proper time is going to be different in different heights, and the Schrödinger equation on the left hand side is like d and dt, an absolute time. So here you have a relative time different at each height. So which time you want to use? Okay. So again, the experimentalists say, "Oh, we're not worried about it at all, Ivette, because we just use the time at the center of the trap." That doesn't work that well, and it's like it's a patch. But forget about it. Let's say maybe for what they want to do, it's good enough. I don't know. But from a theoretical point of view, this is not the right thing to do. But you're actually losing on the possibility of learning what we should be doing, because this is really a very good example where you are at these stages where quantum mechanics and general relativity interplay, but we don't have a theory to describe that experiment. So what I was telling, I recently went and visited the group at NPL, at the National Physics Laboratory, and I was having a little discussion about this, and I was telling them, that we don't have experiments to address these questions, and now you're having an experiment that actually is getting there. So let's use this experiment to try. So you have a theory. That's good. The theory is that you're using is that you say, well, I can more or less do with taking the proper time at the center of my, of my sample. Well, if you want to be rigorous, really what you have is that you lost your notion of time, of clock time. And you need to come up with a new thing. But that is what opens the opportunity of, You came up with a theory which is not very good, I think, which is measuring at the center.
Well, you mentioned theoretical problems, but it sounds like what you're describing is more akin to missed opportunities for probing the interaction of general relativity with quantum theory.
Yes, both in a way, right? I mean, what I was trying to explain to them is that as a theoretician, we don't have a proper theory to explain your experiment. Now, your experiment is an experiment. An experiment is the experiment, right? It's like, in that sense, it's not wrong. What is wrong is the theory that we're using to describe your experiment, but you need to start somewhere. Again, the little circle that we talked about. So I start with a theory that's not very good. Then you do the experiment. We looked at the experimental results, and then I come up with a way of modifying my theory. Yeah. So right now I have a PhD student working on this problem that I like very much. And we've made some progress before, not with atoms, but with light. I want to show you more or less what we did before.
Please.
So Einstein came up with this idea of the Einstein light clock. So he used this clock, this idea of a clock, to argue things for relativity and so on. So he considered two mirrors and then a photon bouncing back and forth, and that gave you the tickings of the clock. And then he talked about what happens if you move this clock and so on. But now we can use quantum field theory and quantum optics to quantize the idea of Einstein's clock. So I've done that. I wrote another series of papers in that direction, is to say, okay, now I have two mirrors, but I have a quantum electromagnetic field inside. So I get when you do that, you get sort of the field you can write down as an infinite sum of different modes. So those are states that are sharp in frequency, but the photons are completely delocalized in your box. But you can use quantum field theory to describe that. So that was also a long journey, because when I started to work with that, you could only do this in flat space. And the only motion that people could describe was a sinusoidal motion of the walls, and this was the dynamical Casimir effect. But I wanted to do more than that. I wanted to consider curved space from the Earth to a planet and send the little box up to study how the curvature, the underlying curvature of the Earth would affect the quantum clock, or how would like an interplay of quantum states with time dilation would look like, and all that sort of thing. And gosh, that was really, really hard, because solving those equations was very complicated. And what allowed me to make progress was working with Jor Maluco, a colleague in Nottingham, where I used to work, who is an expert in quantum field theory and curved spacetime. And then, we managed to come up with a new methodology where we could now start, let's say, solving those sort of problems in a more general way. And then I had a student and a postdoc that helped me generalize this to curved space and so on. And then, so we have a clock model, which is basically Einstein's light clock, but with a quantum field. We fix a frequency, and the oscillations of the quantum states of this frequency mode give you like the ticking of the clock. But now we can move that in curved space and ask questions about the interplay of time dilation with quantum things. And we found some interesting things, like when you move the clock, due to things like called the dynamical Casimir effect, you create particles like photons inside the clock, and these affect time dilation.
Interesting.
So it's kind of fun doing that,
Yeah.
Again, I don't think you go to the very fundamental questions by doing it, but it's you start learning certain things. And one of the things I was interested in is that, if you use these clocks to measure space and time, or time dilation and so on, because the state of the field is a quantum field, then you start getting into these uncertainty principles, things that you can actually not measure space and time with infinite precision. Like if you measure time very precisely, then space is not, and this sort of thing. So I wanted to explore more the, let's say, the constraints that you get by in measuring space-time by using a quantum system.
Usually when people speak about Heisenberg's uncertainty, they're talking about position and momentum, and you're talking about space and time.
Well, I mean, you could... they don't go together, no? So you have energy and time, and then momentum and position.
Yes.
But in these clocks, you have sort of an interplay of things. You have states that are obey minimum uncertainty in space and momentum, so they're called Gaussian states, coherent states. And then we move these in space, and then you have constraints that come also from the energy and the time. So I didn't kind of go into much detail. I wasn't very precise when I said that. But you start getting the role of the different uncertainty principles that you get from quantum theory, playing a role in how well your clock works and things like that, which is very interesting.
Cool. This work goes back to 2014.
Yeah.
So I'll leave a link to all of the articles that have been mentioned in this talk, either visually or just audibly, in the description. So people, if you're interested, you can read more.
Yes, this is how we got started. So this first paper was in flat space, but now, this is the latest paper that was published about clocks, that was published in 2023. There we can now, since we managed to, let's say, generalize our techniques to include curved spacetime. It sounds simple, but literally it took us more than 15 years to be able to do that. And we're using quantum field theory in curved spacetime. So then we finally had some, theoretical methodologies that allow us to address that question. And what we did is we looked at a clock, a light clock, but we now were able to describe the clock in the space-time of the Earth, treating the space-time of the Earth like with the Schwarzschild metric, and come up with a model of a clock and discuss how the clock ticks, and talk about the Schwarzschild radius of the Earth and how does this show up in the face of the clock and so on. So that was
interesting.
We then came up with a notion of clock time already in this clock. At each slice within the clock, the proper time is different. And we said, okay, but you could still build a clock by looking at the collective oscillations. And that gave me an idea that, okay, now maybe we can go back to the atoms and redefine the notion of the clock time using the collective oscillations and so on. But this is a student of mine is working on that. And we don't, we're just starting. Like, we don't really have much to say about the atomic case yet.
All right.
Okay, so now the last thing I want to talk about with respect to these experiments is mass. So, I was telling you how Roger proposed many years ago that if you have a massive superposition, this is unstable. And he argued that by showing that there was a conflict between the superposition principle and the equivalence principle. So he said, yes, you could have a superposition of a massive system that for him, this would already be quantum gravity because you have a gravitational field in a superposition of two different configurations, but these are unstable and they decay very quickly. And that is why we don't see superposition in the classical world. So what kind of masses would you need to, in order to see if the predictions of Roger are correct or not?
Do you mind briefly outlining why is it that the superposition contradicts the equivalence principle or the strong equivalence principle?
Yes. So he starts by describing a mass that is in a superposition that is falling. And then he says, okay, if you describe the situation from a Newtonian point of view, and he writes like the wave function, and now from an Einsteinian point of view, and he writes like a different equation. So he says these wave functions have to be the same up to a phase. No, because in quantum theory, states, wave functions are equivalent up to a phase. So, but you see, his whole argument, I'm going to show you a paper that I wrote with Roger in the next slide. And in that paper, we write an introduction where we go through Roger's arguments, but they're not necessarily simple. And one of the reasons why is because we don't have a theory for that. So Roger makes arguments that are like good arguments, well informed, but without actually having a theory. So sometimes the arguments are talking about quantum field theory and Curt spacetime, and then he might make a Newtonian approximation and so on. But he shows that the Einsteinian point of view is different from the Newtonian point of view, and that there is a contradiction there, and that then because of that, he argues that these superpositions should be short-lived. And he goes beyond that because he gives you a formula that measures sort of the error. And this gives you an energy uncertainty. And it's related to the gravitational self-energy of the difference in the superposition. So you take some... Maybe that is maybe going more technical, but we can if you want to, because I know that your followers are quite well educated in physics. So let me jump and then I come back a little bit here.
Sure.
This is the paper that I mentioned that I wrote with Roger. And what we did in this paper is that we calculated, how massive would these superpositions have to be if we use the Bose-Einstein Condenstate. I'm going to come back to that. But we found that you need at least something like 10 to the 9 atoms in a superposition. And let me tell you where the field is now. So, people started to put electrons in a superposition of two different locations using like a double slit experiment. Maybe 90 years ago. I don't remember when was the first experiment with electrons. And from there, they said, okay, it works for electrons. Amazing. Let's do it now with atoms. And, then it's like, how bigger can the states, the system gets. And the record is held by Markus Arndt's group in the University of Vienna as well, where he has been able to put big molecules in a superposition. And by big, I mean the molecules have around 2,000 atoms.
Wow.
But for gravity to act, you need at least 10 to the 9. Actually, for molecules, you need even more. So you can see we're very far from that.
What do you mean for gravity to act? I thought the assumption is that gravity acts as long as you have mass. Don't these have masses?
Yes, but these are stable superpositions. No,
according to the calculation from Penrose?
Yes, Marcus showed that you can have these superpositions, and I think they lasted milliseconds. I don't exactly remember how long he had them for. So they are stable for that long in the lab. So gravity is not causing the collapse of superpositions at those scales.
I see.
But now the question is Roger right? Because if Roger is right, then that explains why we don't see superpositions in the macroscopic world. And what would be super interesting is to see that, that is a big open question in fundamental quantum mechanics, is to understand what takes you from quantum states being in superpositions to the classical world where we don't see quantum superpositions. It's a very interesting question. Marcus and many other people are trying to address this question in an experimental point of view from the experiment by trying to put more mass into the superpositions. There are many different experiments going on at the moment, and they use, for example, nanoparticles, nanobeads made of silicon or silicia, diamonds, little mirrors, rods, even membranes. There's many experiments going on. And also a record has been held by Markus Aspenmeier, also in Vienna. So I spent 3 years in Vienna because of these amazing people and experiments there. So I was very lucky to get a visiting professorship for that long and be in the same environment where these amazing scientists are. And so Marcus was able to bring one of these nanobeads to the quantum regime by cooling it down to lower vibrational states. So they're already in the quantum, let's say, scales, but with 10 to the 8 atomic masses, so quite a big bead. But he cannot put them yet into a superposition of two different locations. That has not been possible. Also, one of my colleagues I'm in Southampton, so one of my colleagues there, Hendrik Ulbrich, also has a very recent amazing paper where he takes these little beads and he manages to measure gravity. But this is all classical. But anyway, I mean, at those scales where quantum starts to kick in, well, what he wants to do is push these experiments so that maybe he sees some quantum gravity, still far from that, but let's say approaching. But this is where things are at with respect to the experiments with big mass. So what I did with Roger is that when he started to tell me about his proposal and the experiments that people were doing, I noticed that all of these experiments were using solids, mirrors, beads, and so on. And it's very difficult to cool a solid to the to very cold temperatures where you have little noise. So they haven't been able to make more progress because of the noise, because you can't cool them enough. Now, a Bose-Einstein Condenstate is a really beautiful system. I think it's my favorite system because you can reach 0.5 nanokelvin, like the coldest things that we can do. And you can get up to 10 to the atoms. I mean, that's not very common, but there's been an experiment using hydrogen in which they cool 10 to the 10 atoms into a condensate. So let me tell you a little bit what a condensate is. So you have let's say, when you learn quantum mechanics, you learn that if you put a particle in a potential, well, the particle is there moving in the potential. But if you cool it to the ground state, it will, let's say if you manage to the ground state, the atom will be completely delocalized within the potential. So you don't know what the position of the atom is in that whole thing. No, that's really, I don't know, when I did that in quantum mechanics, I loved it.
Mm-hmm.
Now think about having 10 to the 8, 10 to the 10 atoms all cool down. But atoms are bosons, so they can all occupy the same quantum state. So you can cool them all down to the ground state. And that is what is called a Bose-Einstein Condenstate. So you have the biggest system that behaves in a quantum mechanical way. And like I said, in the experiment, people have been able to cool these systems to 0.5 nanokelvin.
Right.
So I was wondering if then this would be a good system to test Roger's predictions. And that's what we did together. We said, okay, how would it go with a Bose-Einstein condensate? And also super complicated, because you would have to create a superposition of all the atoms on the left with all the atoms on the right. And although the temperatures are that low, people have not been able to create these superpositions. They're called noon states because you have N, 0, 0, N.
Yes,
no?
Cool.
And you know what? The record is by one of my colleagues called Chris Westbrook, and he's been able to do 2 atoms. And so you can have many, you can have up to 10 to the, you can have many atoms in quantum states in a Bose-Einstein condensate, but not many atoms in a spatial superposition of 2 different space locations. That's where gravity acts.
Uh-huh.
So this is what I now have been working on in the last 2 years. And it's not related to, it's inspired by this work with Roger, but it's a complete new thing. I hope I can talk about it at a later time with you. But in that previous paper with Roger, we studied things like Roger had given formulas for uniform spheres, and in a BC you could have pancakes or elongated BCs with different distributions of the density, and we studied if these would enhance the effects predicted by Roger. And then, you have a lot of losses, and we studied the losses and so on. And that's how we came up with this. Well, with a BC, you need at least 10 to the 9 particles, maybe even 10 to the 10, in order to start being able to actually verify that the energy uncertainty of gravitational origin that Roger predicts has an effect. So now I'm going to finish this part with the slides, just telling you of an example of the work that I've done, where I brought together quantum field theory and curved spacetime to, let's say, propose a new sensor. And it was quite bold, because I came up with a proposal that you could use a Bose-Einstein condensate. So let's say the sample itself can be 100 micrometers, 50 micrometers, the cloud of atoms.
Sure.
And the experiment is, again, a tabletop experiment. We could put it in this room, no?
Cool.
And I claim that you could use the BC, because you see, an atom, we saw how precise they are. And a BC, you might want to see it as 10 to the 8 atoms cooled down to the ground state. So this is a very precise, it's a system that is very sensitive to space-time distortions. And I made a proposal on how could you use the system to detect gravitational waves.
Wow.
And it's quite crazy, because gravitational waves are detected in LIGO, where the apparatus measures, each arm 3 kilometers. So this is very bold. And I've been really when I met Roger, that was in 2017, I was really invested in that and trying to convince, the community that you need to do this experiment, because it really opens up a new direction. And Roger was trying to convince me to work on the collapse of the wave function due to gravity. I was very reluctant, because I thought, no, I want to put my time and my energy into these. And after the years, Roger managed to pull me more into what he's doing. But yeah. So when you talk about using atoms to measure gravity, what we usually do in quantum technologies is an atom interferometer. So let's say you have a atom and you hit it with a laser, with a photon, and you make the atom, you put it in a superposition of two different positions, but they're free falling. So they follow different trajectories, and then you recombine them with lasers, and they recombine at a point. But because they went through different trajectories, they pick information in a phase that depends on the local gravitational field. And this is what a quantum gravimeter is.
Interesting.
And I put here a single particle detector because although they throw maybe 10 to the 6 atoms at once into the interferometer, all the atoms are independent. And each atom goes through this superposition of trajectories, and then they interfere at a point. So I put here the interference is local because it's at the point where they recombine. And then this is limited by the time of flight. And the equation is very simple. It's just this equation that's here. Basically, it depends with the time of flight squared, which means the bigger the detector, the more precise it is. That's why LIGO is so big. And they're thinking, because they want to go to, well, LIGO is with light, but the principle is the same. They now want to make a bigger detector in space called LISA to have more precision. So a lot in physics, the tendency is to go very big experiments. Of course, they're very expensive. And my husband says that I'm a rebel because if everybody's doing one thing, I always want to do something different. That applies to everything in my life.
Yeah, that's another aspect that unifies us.
Yeah, really? Yeah, no, it's like
I'm a contrarian at heart.
Yeah, exactly. So if everybody wants to make big detectors, I want to make them very small and so on. But it has paid off for me in science. Maybe sometimes in life can make me like a Grinch in Christmas and things like that. Because I was like, I don't want to do what everybody does. So socially, I don't want to go to the movie that everybody's watching. But in science, it's been
interesting. Yeah,
it's been good, So here I also write that this is compatible with Newtonian gravity because this is an experiment that is described with the Schrödinger equation. And if you treat the local gravitational field by Newtonian gravity, everything works very nicely. And like I said, these are already commercial. My colleague, Philippe Boyer, has founded a company that he now sold called Mucons. And there are other, like Mark Kasevich does that as well, in which, they build these interferometers, these gravimeters, and they sell them. They're like a meter big, I think, and so on. And that's like, you cannot make them smaller than that because then you lose precision. So if you want to get atom interferometers to apply them to fundamental physics, to learn about the equivalence principle or to measure anything respect to gravity, and so you want to make them more precise, you have to make them bigger. So Philippe Boyer did this amazing experiment in which he put his atom interferometer in a plane. So he flew the plane as well and let it in free fall for a bit to get the long baselines. He also has an amazing experiment under ground called, I forgot the name of it now, but it is like the arms of the atom interferometer are 300 meters long. So this is huge. You can see here sort of the tunnels and so on. And in Germany, you have a drop tower. That is like, what is it like this? Like
a drop tower.
So they put up here.
Okay.
Oh, a drop tower. They put up there like an atom interferometer, and then they let it drop to get these long interferometer arms and be able to be more precise. Some other people, also look at these atom interferometries and put lasers and slow down the atoms so that they get. So, for example, this paper by Guillermino Tino is really beautiful, trying to miniaturize the detectors. So what I came up with this idea was, well, if you're trying to do interferometry in using these sort of, call it spatial interferometry, because the atom goes through two different positions, the precision is going to be limited by how big it is. So you're going to have to make them bigger to be more precise. But if instead of that we do interferometry not in space but in frequency, then what is going to limit your precision is time. So the states, the sensor can be very small, but you're going to have to produce quantum states that live longer in time. So with this idea that I called frequency interferometry, I came up with a number of sensors, and including the gravitational wave detector. And then I applied it to searches for dark energy, searches for dark matter. I also patented an idea on how to use these states to measure the local gravitational field. So this might have commercial applications in the future. And I like that because I like more fundamental questions. Actually, my favorite question is like, what's the nature of reality? What are we doing here? Where am I?
It's a dangerous question, huh?
Yeah. Very. All of these things. But, when you're doing that and you find some interesting things, why not also come up with something that can be, patented and commercialized and so on. Then when I met Roger, I was really invested in this. And I'm still working on it. I have some recent results. One of them it was in the old slides. It doesn't matter. But I think I managed to give you a flavor of what you can do by bringing together quantum technologies and apply them to fundamental questions and where things are at. I think I want to finish by saying that this last proposal is an example where we used not quantum mechanics, but let's say a more fundamental theory, because it takes into account relativity, which is quantum field theory in curved spacetime. And although it's not the finished theory, because it cannot address the question of superpositions of mass, you can apply it without problem to specific cases like the propagation of space-time, of packages in the space-time of the Earth, and many other interesting instances. This allows you to come up with, let's say, new sensors. And the theoretical predictions that we've made is that these sensors are so, in principle, they still have to test them, so precise that you might be able to detect a gravitational wave with a tiny system. And these are for high frequencies, by the way. They don't really compete with LIGO, because LIGO works in a different frequency regime. This would be for frequencies higher than the ones that LIGO detects. But, let's say using these patches of the theory that incorporate relativity, I think already show you that you can, in principle, make sensors that allow you to go closer to these scales where I was talking about that we don't have the guide to unify. No, when people were trying to detect gravitational waves, the first apparatus that were built in Maryland, you can still see them. There are these Weber bars. So people predicted. Weber predicted that the phonons, so the vibrational modes of these big metallic bars, would resonate with gravitational waves. And then he claimed that he actually had detected one. And then this got sort of controversial and then eventually disproved. But actually, the proposal that we made, in which you can implement it by using a BEC and using the vibrational modes, like the phonon modes of the BEC. But because you can cool the BEC to half a nanokelvin, that is 10 orders of magnitude cooler than the Weber bars were cooled initially, then you can prepare the phonons in a highly quantum state, which you cannot do unless you go to those cold temperatures. And then you can exploit all the sensitivities that we were talking about, quantum technologies, to see changes in the space-time. And that's how we came up with that proposal. I think I can talk forever, so maybe it's good to leave it here. I think let's see if I had like some kind of concluding. Well, yes, my concluding slide was to say that I've managed to raise funding to build a new experiment. So I'm working with Chris Boyer, Philippe Boyer and Chris Westbrook, who are going to test some of my predictions in a new proposal that I have for unifying quantum theory and gravity. And well, we're still like, working very closely with Roger. So I'm very excited because it's like a new era for me now, being able to work this close with the experiments. And yeah, I'll leave it here.
Professor, thank you so much. You've given far more than just a flavor. I lost count of how many pioneering ideas there are here with actual practical consequences in the near term being within a couple years. I don't recall the last time that's happened on this channel, and all I do is interview people that are at the bleeding edge in their field. So thank you for that.
Thank you. Thanks. Yeah, no, thank you. It's a big pleasure for me to be on your channel.
The pleasure's all mine. Thank you.
Great, thanks.
Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. There's now a website, curtjaimungal.org, and that has a mailing list. The reason being that large platforms like YouTube, like Patreon, they can disable you for whatever reason, whenever they like. That's just part of the terms of service. Now, a direct mailing list ensures that I have an untrammeled communication with you. Plus, soon I'll be releasing a one-page PDF of my top 10 toes. It's not as Quentin Tarantino as it sounds like. Secondly, if you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook, or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for theories of everything, where people explicate toes, they disagree respectfully about theories, and build as a community our own toe. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in theories of everything and you'll find it. Personally, I gained from rewatching lectures and podcasts. I also read in the comments that, hey, toe listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/CurtJaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on Toe full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.